Welcome to our Senior Design 2. We are Team 13, and we are Jack Hobbs, myself, Jai, Josh, and Cameron. We decided that we would want to create an active aerodynamic system for a remote control scaled vehicle. And we are really excited to share with you what we did this semester. So our objective and our motivation was to create a system that utilized a Raspberry Pi to control an autonomous aerodynamic package for our remote control scale car. We chose a remote control scale car because it's cheap and relatively simple to implement, and the parts are widely available at this size. And our motivation goes back to all of us being car people. We love vehicles and the systems that surround them, and being electrical and computer engineers, we're very involved with the creation of vehicles. So naturally, we wanted to test our capability at creating a system to make a car handle better and go faster at the end of the day. Our project goals and deliverables. So our first project goal was an active aerodynamic components can perform advanced movements based on accelerometer data. So this is the pitch and roll of the aerodynamic wings that you will see later in the project. All steering and acceleration and deceleration functions are user controlled, meaning that the remote control car is not autonomous. It is controlled by the human being. But the aerodynamic components are controlled autonomously through the Raspberry Pi. All of the components were firmly mounted to the vehicle chassis and then covered entirely by the vehicle body. This was to ensure maximum aerodynamic efficiency and to ensure that our wires were not flying around everywhere while we were testing. We wanted to perform wind tunnel testing, and we wanted to receive concise results. And then we wanted to present demonstrating the testing and measured results to prove our concept. So why aerodynamics? Why are aerodynamics important to vehicles? It's incredibly important. Aerodynamics allows for vehicles to be more efficient, save on gas, to perform better, be more stable while cruising at high speeds, a myriad of different reasons. But for our use case specifically was to provide more downforce in a turning event. So as you can see on your screen, a drag reduction system is off, meaning that the wing is up. So the wing is up and providing the most maximum downforce. You can see on the top picture, the turbulent wind is being directed up and away from the car and pushing down very, very hard on the car. Now, on the bottom picture, the drag reduction system is off, meaning that the wing is closed, or in this case, smooth across the body. And you can see the wind behind the car is much shorter in its peak, meaning that the wind is gliding very smoothly across the car. And if you can see, the low pressure zone underneath that high arching wind is much lower to the ground, which is pulling the car to the ground. And this concept is how cars can produce more downforce to, in turn, have more grip because the normal force is higher around a turn. So just like the previous picture, we did this with ours. So these pictures are located in the wind tunnel that we utilized to test. So the top picture is the drag reduction system on. Our wing is closed, meaning that it is not providing any extra downforce. And you can see the wind glides very smoothly and efficiently over the vehicle. And you can't see any movement along the wind or downforce or low pressure zones. On the bottom, you can see both of our wings are extended. So we decided to utilize two wings on our vehicle. This was a rear mounted deck lid wing and a roof mounted wing. And as you can see in the lower picture on your screen, you can see a very, very clear representation of the angle that the wing is able to reach. And as the wind hits the wing, it produces massive amounts of downforce by forcing the wind up and very smooth lines back afterwards. And then again, a low pressure zone behind the vehicle when the wings are raised, sucking the vehicle to the ground, providing even more downforce.
For the early prototype, you can see we started with just a clear like sand shell, typical of any RC car body, and the main peripheral control board, which handles all of the physical inputs and outputs from sensors or out to the servos, which interfaces directly with the Raspberry Pi. The main system is controlled by an MPU 6050 accelerometer and gyroscope, which has been designed around the manufacturer specification to be able to interface directly with the Raspberry Pi using the I2C interface. There's also a 40-pin connector to allow everything to mesh over perfectly with the Pi. And then to control the outputs with the servos, it's a PCA 9685 PWM driver, which we're using 4 of the outputs of to be able to control our 4 servos with 2 for each wing. The board also has reverse voltage protection to prevent, in the case the battery is connected in reverse direction, nothing will blow up. And then we also have our main block diagram for how our system works. So all of the drive components are handled by the RF receiver and the radio standard with the RC car to handle the motor driver and the motor and the steering servo, while the Raspberry Pi takes in data from the accelerometer and the gyroscope to get things such as vehicle forward speed and the tilt angle, which can then write telemetry data to our app interface or to the onboard SD card of the Pi, and then also writes the outputs to the aerodynamic components through the PCA 9685.
So for our hardware design requirements, we needed to have at least 2 moving aerodynamic modifications, and we should have seen visual time differences in our lap performance, along with visualization of the aerodynamic effects within a wind tunnel, which you saw on previous slides. We also wanted at least 30 degrees of movement from each of our wings, so a fully extended angle of 30 degrees or more. And we wanted to consume our aerodynamic components to consume no more than 3,000 milliamp hours in 30 minutes, which is about the approximate size of the batteries that we were going to be using. And we wanted all peripheral sensors and everything integrated into the control board, so nothing standalone, everything integrated into one circuit. We created a custom peripheral board, which you saw on the previous slides. That way we could consolidate our accelerometer and gyroscope and all of our connections into one single board. That way we can minimize our cable runs that we had to do. We also made sure that all of our processing was taking place on our Raspberry Pi, and that all of our wing movement was using linear servo motors. And also that a separate power source was used to run board electronics than to run the car itself.
So when thinking about the requirements for our software, we wanted our software to be able to perform all of the calculations and decision making on the Raspberry Pi during driving. And we wanted a easy to use GUI to provide a view of telemetry and to manually adjust the wing angles if needed. Additionally, we wanted to get as many telemetry logs as we could and store all the data for more analysis. So to address this, we ended up creating software that just takes input from the accelerometer and gyroscope on our custom peripheral board, and it makes inferences off that data to move the angle of the wings according to the thresholds we've set. So the software we chose to write primarily in Python for its flexibility, especially for this use when we have a GUI involved, and we wanted a learning opportunity to have more experience with the language. So speaking of the GUI, we ended up using a web-based GUI so we can access it via any mobile device. So to do this, we used Flask API calls to our main control module to control the wings. And doing this, you could launch a hotspot from the Raspberry Pi, make it like an access point, connect to that hotspot, and then even if you're on the track for testing, you can be able to control and see the telemetry of the car as it's driving.
This project relates to the long-standing principle of more downforce allows the vehicle or race car to corner faster. So the faster a vehicle can turn around, usually the greater chance of them winning the race. So this is very applicable to race cars and our car in particular. So the idea from active aerodynamics stems from the principle that the vehicles need less downforce on the straightaways, because more downforce means that the vehicle has less top speed. So this is why we wanted to create an active system so that the driver, quote unquote, did not need to manually adjust this. It would simply do it automatically. We had wonderful visualization of the aerodynamic principles in the wind tunnel. It was truly special. to see all of that amazing visualization and the lap times. So the car with aerodynamics, without aerodynamics, excuse me, had an average time over 5 laps of 16.25 seconds at the racetrack we attended with a weight of 3,050 grams. The car with aerodynamics had an average time of 16.75 seconds with a weight of 3,402 grams. We feel these weights are comparable enough. We had a anonymous test driver come and drive both cars without knowledge of which was which. And we asked them to provide information and opinions based upon the driving, and they determined that the car with aerodynamics felt more stable. And our downforce calculation, using the downforce formula, we determined that the downforce of our wing provides roughly 1.1 newtons of downforce, which for this size and scale is quite impressive. So in conclusion, the addition of aerodynamic components to a remote control car can be visualized and felt. This was our main priority with this, is that if we were to create an aerodynamic system, would the results be able to be visualized and felt? The answer to that question was yes. The interpretation of our data may have been skewed due to improper testing environments. We were extremely limited to the space, and we only had very limited time at a track that was set up for high speed, low downforce cars, which is why our vehicle with more aerodynamics actually had a slower speed, because our car was adding aerodynamics to a track that really didn't need downforce. But that was, again, the only place that we had any chance to test as far as space goes. The integration of a peripheral board and Raspberry Pi and software proved to be a great success, with quick, efficient actuation of the wing, and great decision making. And the utilization of the onboard Wi-Fi connection allowed us to have a mobile GUI to control all of our components wirelessly, and it also looks quite good. So we really appreciate all the time and energy all of our professors provided and helped us along this journey, and we look forward to showcasing this to everyone on Wednesday.